Hi everyone. In this bonus video for the chain rule, we're going to look at Calculus 1 rules. So for example, the product rule or the exponential rule, and see how they actually follow as consequences of the multivariable chain rule. So this is a nice example where the more tools you learn, the more mathematics you learn, the better insight you have onto previous knowledge. So the better insight you have here onto the product rule and the exponential rule as to why they should even be true. Why should they be true based on higher level results? So let's have a look at these two rules. So the product rule says that the derivative of the product is the derivative of the first function times the second plus the first times the derivative of the second. We proved this in Calculus 1 using the definition of the derivative in terms of a limit, but we'll see here how it also follows as a consequence of the multivariable chain rule as applied to a particular kind of multivariable function. In particular, the product function is what we'll use to prove this one. We also have the exponential rule. Now you may not remember this exponential rule by name or even by this formula. What you may remember is some examples that we did of this form. So in one of the lectures, and I'll link to it below, we worked out, so in Calculus 1 we worked out what the derivative of x to the x squared is. And the way we did that was we took the logarithm of both sides and we did implicit differentiation. But that would be an example of a function where we could use this exponential rule. In general, the exponential rule says that whenever you have a function of x raised to the power of another function of x, then you can compute the derivative in this way. And it looks quite complicated, but we're going to see, looking at it through the lens of multivariable functions, that it seems quite reasonable that this is the form it would take. So let's show these follow from the chain rule. Okay, so we're proving Calculus 1 results from Calculus 2 or Calculus 3 tools. So the product rule. Well, the way we're going to deal with this is we're going to want to differentiate a product of two things with respect to x. So I will just call those two functions u and v. And in particular, I'm going to think of this now as a multivariable function. So this is where the multivariable calculus comes into it. I'm thinking of u times v as just a function of two variables. So I'll call it p of uv, p for product. The chain rule tells us that it is the partial derivative of p with respect to u times the derivative of u with respect to x plus the partial of p with respect to v times the derivative of v with respect to x. So that's by the chain rule. So we've just used the chain rule to differentiate a product of two variables u and v. And I claim that this is just the product rule. And we can see why, because what's dp du? dp du, well, p is u times v, so dp du is just v. So it's v du dx plus dp dv, which is u dv dx. And that's the product rule. So we just derived the product rule from the multivariable chain rule. Let's see how we can do the same thing for the exponential rule. So the exponential rule says we want to differentiate, well, it's one function raised to the power of another one. So I'm going to first write it down as a multivariable function. So what's the form of this? It's something raised to the power of something else. And so that's going to be the form that I'm trying to differentiate. So I'll call that capital E of uv. Just like I use p above to represent the product of u and v, I'm going to use capital E to represent the exponent, u to the power of v. And so we're going to use the chain rule again. So this would be the derivative of u with respect to, the derivative of e with respect to u times du dx plus the derivative of e with respect to v times dv dx. And that is by the chain rule. And now we can go ahead and use the fact that capital E of uv is this specific function, this function of u raised to the power of v. So what is d e du? What is that partial derivative? So there we're looking at u to the power of v, where I'm treating u as the variable and v as the constant. So v comes down, becomes u to the v minus 1, and then that's times du dx. And then we add to that the derivative of e with respect to v, where we're treating v as the variable and u as the constant. So in this case, you can kind of think, if u is the constant and v is the variable, it's like 2 to the power of x or something like that. So I'm differentiating a constant raised to the power of a variable. So we can kind of think of something like that, or e to the power of x. The problem with e to the power of x is it doesn't give us the most general form. So u to the power of v, u is a constant, v is the variable. So that would be, the derivative would be u to the power of v times ln of u. Again, just think of something like this. How would I differentiate that? 2 to the power of x. It would be 2 to the power of x ln of 2. So that's all I've done here. I'm thinking of u as being that constant, v as being the variable. And then I multiply by dv dx. And that is precisely that exponential rule that I wrote above. The derivative of u to the power of v is, and then we've got these two pieces. One piece, we treat u as the variable and v as the constant. And then in the next piece, we treat u as the constant and v as the variable. But that's our exponential rule. We've just verified it using the chain rule. So let's go back to that example that we had above. So we'll go back to that example. Y equals x to the power of x squared. So again, we've done this one in Calculus 1, and I'll put the link to the lecture from Calculus 1 where we do this using logarithmic differentiation. I'll put it in the description below. But let's see how we can do it using this exponential rule in its full form, where we just verified it using the chain rule. And I don't need to think about this formula when I do it. What I can do is I can just think about how I did it using the chain rule. So I'm going to compute the derivative. So the first thing I do is I think, okay, let's let the base, that x, be the function, and the exponent, x squared, think of that as the constant. So I've got x raised to a constant. And then I'll switch the roles, right? Because I'm thinking of the base being u and the exponent being v, so I'm going to do a partial with respect to u first, and then I'll switch the roles. But here I'm thinking of, okay, I've got x to the power of x squared. First I'm going to think of the x in the base as the function, or the variable, and the exponent as the constant. So I'm going to use the power rule to differentiate that. So there we go. That's that first part. Treating it as x to the power of a constant, and that's how we deal with the constant. And then I'm going to add to that. Now I'm going to switch the roles. I'm going to let the base be the constant now. That x is my constant, and my exponent is the variable, or the function. And so in this case, it's x to the power of x squared. When I differentiate that, it's just x to the power of x squared times log of the base, and then I've got to multiply by the derivative of that exponent, because I was thinking of it as a number, or a constant, raised to the power of x squared. And so that's my function. And so when I do the base x raised to the power of x squared, that derivative, then I have to multiply by the derivative of the inside, which is the derivative of x squared. And so this becomes x squared. Well, I can write it as, I can bring these things together. This is going to be x squared plus 1 plus, and then it's an x squared. The derivative of x squared is 2x, so that would be 2x squared plus 1 ln of x. Or we could write it as x to the x squared times x plus 2x ln of x. And you may say, why did I choose to write it like that? I did have the plus 1s in the exponents. Instead, I seem to factor out the x. The reason I wrote it like this is because this is how we expressed the derivative in the lecture from Calculus 1 when we did this derivative using logarithmic differentiation. So I just want you to see that you get the same result. And hopefully you see that treating it from this perspective was quite a lot easier than it was doing the logarithmic approach. Here we just treated it as some base function, some power function, and we just said for one derivative I'm going to treat the base x as the function and the exponent as a constant, and just differentiate it as if x squared were a constant. And then I'm going to flip the roles and say now treat it where the base, I'm thinking of it as a constant, and the exponent, x squared, is the function, and take that derivative and then add those two things together. And that's really what the chain rule was telling us to do. Alright, so that's it for this bonus section. Thanks for watching, and we'll see you again next time.